Welcome to the grasping tutorial for reBot Arm. Today, I will guide you through using reBot Arm to grasp specific objects. For this tutorial, you need to prepare a camera connected to the end of the robotic arm. We recommend using Orbic S Gemini 2 or RealSense D435i depth camera. First, please open the Seed Studio Wiki official website. Click Getting Started and select the Robotics page. This page contains the grasping demo for reBot Arm. Here you can find complete configuration steps and usage methods. At the bottom there is a GitHub repository including relevant source code. Before starting, please refer to the quick start steps to complete the assembly wiring and motor setup of the robotic arm. Since the wiki is still under maintenance, we will next access the GitHub repository and follow the readme document for environment configuration and usage instructions. First, download the source code to your workspace. Enter the folder and use Conda to complete the environment configuration. This process may take a long time. Next, download the repository for communication with the robotic arm hardware into the SDK folder and install it via pip. Exit to the project folder, then install the depth camera SDK into the environment. The specific SDK to install depends on the brand and model of the depth camera used. Here we use Orbic's Gemini 2, so download Orbic's camera SDK into the environment. If you are using RealSense D435i or another brand of depth camera, please refer to the corresponding depth camera documentation for installation. Before running the program, you can see a YAML file in the config folder, which contains project-related configurations. If you need to customize settings during later use, you can modify the configurations here. Next, we need to perform hand-eye calibration of the robotic arm. Before calibration, we can run a small program to test the target detection function of the depth camera. Connect the camera to the computer and run the object_detection.py program. The target detection function is based on the YOLO model. If the model specified in the YAML file has not been installed previously, it will be installed automatically when running for the first time. For more model options, please refer to the information in the documentation. Place a banana in front of the camera, and you can see that the depth camera accurately recognizes the object and estimates its position relative to the camera. Next, we will start hand-eye calibration. First, print the Iruko marker from the folder onto A4 paper and place it on the table in front of the robotic arm. Please note that the size of the Iruko marker must be consistent with the definition in the YAML file. running the program, the robotic arm will automatically move to 50 fixed points to try to recognize the irregular marker. If fewer than 5 markers are recognized among these 50 fixed points, the calibration fails. After the program ends, it will automatically calculate the parameters. It is recommended that the number of valid collections be more than 15. After calibration, we can run a grasping test program to test the performance of grasping pose estimation. This grasping pose estimation is based on YOLO's estimation of the object's long axis, and the shortest axis of the object is taken as the grasping pose. The green box in the video represents the recognized object. The blue box is the estimated minimum and closing rectangle of the object. The red dot represents the object's center, and the white line represents the grasping pose. Next, we will enable the grasping program. Please note that during the grasping process, no one should enter the working range of the robotic arm. If an accident occurs during grasping, please cut off the power in time. When the robotic arm recognizes an object within the working space, press G to make the robotic arm perform the grasping operation. After the robotic arm completes grasping, press Q to release the object, and the robotic arm will return to the origin. We can also use the dry run to make the robotic arm only perform grasping estimation without actual grasping. We also provide another grasping method, which is based on the Graspnet-Baseline model for grasping pose estimation, thereby achieving a more intuitive and higher precision grasping method. First, we need to configure the environment. Please refer to the documentation to download the corresponding dependency packages. Please note that errors may occur during the configuration process. In this case, you need to reconfigure the CUDA path. And then complete the configuration. Next, we need to obtain the Graspnet model into the folder directory. You can refer to the link in the official GitHub documentation to download the corresponding models. We can run a small program to test the performance of Graspnet. Notice that after pressing G, a 3D image appears with many gripper-shaped objects. Which are the grasping pose estimations for the corresponding objects? The redder the color, the higher the feasibility is estimated to be. Similarly, you can run the grasp.py program with the dry run parameter for testing. Then, directly run the grasp.py program to realize object grasping based on Graspnet-Baseline. Thank you for watching.